Hey there, you math-loving people out there, and welcome on my channel. My name's Frank, and in this video I will show you how to use the function fmincon from MATLAB to compute the optimal control of an ordinary differential equation. As always, you should know some basic stuff like analysis. You should have seen an ordinary differential equation before. You should know a little bit about numerical mathematics, like how to structure data and stuff like that. And of course, it's good if you have some experience with MATLAB. So let's jump right into our issue, our problem. Here you can see an optimal control problem. Let's take a look at this. So here you have our ordinary differential equation. So the time derivative of our function y should equal f applied to y. This here is an additional parameter, and this is called the control. So y is called the state vector, and u is the control vector or function in this case. And we will compute the function u to actually steer our system in an optimal way. So this is our ODE, and let's take a look at the objective functional. The objective functional is our goal we want to minimize. So this consists of a function j, which actually only takes the control, because the control is what we want to minimize. We want to minimize the costs of the control in a certain way, which we will define later. For now, this is just contained in an arbitrary function j, and we want to minimize this over the whole time interval, so from 0 to big T. To make things more complicated or more interesting, put it that way, I added some additional constraints. So we have two additional constraints. So the first one is y at a point 0. So our state at point 0 should be g0 under some function g. This function g might look arbitrary and a little bit out of box here, but we see later why this is a good idea to put a function g here. If you feel unsure about this function g, just for now, just take g to be the identity. Don't worry about g. This will be clear later what the function g is actually good for. So the first additional constraint here says, okay, at time 0, our system should satisfy some state g0. The second one is more interesting because it says that at the end of our time interval, our system should be at the point g of t under the function g. And this is a quite interesting constraint because, well, you will see later. So now, this is our optimal control problem we want to solve. Let's take a little bit more into detail. Again, we have our state. This maps to the space Rn. The control maps to a different space. This maps to the space Rm. Well, and the other definitions. And here have our additional function g, our objective function of j. And well, now we have established, or now we have defined our optimal control problem. And now I will show you how to actually solve this problem using MATLAB. Let's start directly with the second state constraint. G applied to y applied to t should equal g of t. So this is our state constraint at the end of the time interval. This kind of looks fishy. We don't like it. And the question is, can we make it? Can we reformulate, or can we approximate this constraint in such a way that it is more easier and more accessible to our algorithm? And I'm pretty sure you've seen the next step. Next step we're gonna do. I've seen this before. We just introduce a penalty function. The penalty function takes two arguments, the state y and our constraint parameter g of t. And what we do now, we just apply g, y, and subtract this with the gt. So basically just bring g of t to the other side and compute the offset, so the difference to 0. I mean, this is just a vector, so we're computing it in some Rn space. So this is super easy to compute. And in addition, we introduce a so-called penalty parameter beta. Beta should be chosen big enough, and you'll see in a second why. Because we're now considering the following so-called augmented problem. So again, you have seen this is our optimal control problem, but without the state constraint here. The state constraint is now contained in this penalty parameter, because if this condition is satisfied, so yt applied to g is actually g of t, then this penalty term is 0, and we are just back into our original problem. So we kind of made things easier for us to get rid of this nasty constraints we don't like. We just set up a penalty function, set up beta big enough to have a big penalty if this condition is violated, and we now consider the augmented problem. So the idea is, as I already told you, we solve an easier problem which should be close enough in a certain way to our original problem. And again, I just told you, if this constraint is violated, we have some penalty. And if it is satisfied, the penalty will go to 0, a0, which is actually what we wanted to achieve. Just a small remark. If you use this penalty approach, you're not actually solving the original problem. So you don't get the exact solution to the original problem, you rather get an approximation. How good it is depends on the parameter beta. If beta is like going to infinity, you get a very good approximation, but you lose some properties you gain when beta is small. So the penalty parameter beta should be chosen in a very sophisticated, in a very sensitive way. Let's come to the discretization of our parameters. To do so, we split the time interval, which is given from 0 to t, into n equidistant parts. You can see them here. And the distance of two neighboring time points we call h. And now we actually discretize our function, our control, our state, and our right-hand side of our ODE. And you can see it here. If we evaluate u at a time point ti, we just call it ui. For the state, we call it yi. And for the function f of our ODE, we call it f of I. In fact, these are now vectors, so keep this in mind. We have a multi-valued function u, and if we discretize it at a certain point, or if we evaluate it at certain points, we get some vectors. So keep this in mind. We will use this throughout the whole video, because this is our thing, our discretization we will use in MATLAB actually. So how to get rid of the ODE? Here we use the fundamental theorem of calculus. So we just integrate the time derivative of y from tk to tk plus 1. And using the fundamental theorem of calculus, we end up at yk plus 1 minus yk. So this is nothing special here. But we haven't used our ODE yet. So y prime is actually f. So just plug it in here. So y prime is f. And then we get this right, then we get this equation. So yk plus 1 minus yk is actually the integral over f applied to y and to u. This is actually quite nice, because now we have something to approximate. We can approximate the integral on the right-hand side. And in the following, I will show you 3 different approaches how we can approximate an integral. The first one is very simple. So we have the blue line here is our function we want to look at, and here we have the point a of b, and we want to integrate from a to b over the function f. So the dotted area is the integral we want to compute, or we want to approximate. The first very simple approach is, okay, well, just evaluate f at the point a and multiply it with b minus a. Then you'll get this red area. Of course, this is a rather poor approximation, but this is an approximation. And in a similar way, you can evaluate it at the right-hand side. So you can evaluate it at the point B. Then you end up with this approximation. However, this is just as good or just as bad as this approximation. So what we're going to do now is, well, just take the intermediate value. So we approximate the integral using f of a plus f of b divided by half. So this is the red line here. And multiply it with b minus a. And then we get this integration. So that is approximation of the integral. So a to b of f times ds is just 1/2 b minus a times f of a plus f of b. If you have watched my video about the explicit Euler method, to derive the explicit Euler method, we used this very first approximation. So the integral of f from a to b is b minus a times f of a. So this is a left-handed box rule, something like this. Of course, we could have used another approximation of the integral, for instance, the integral approximation I just presented to you. But we have some certain disadvantages in this case. This will result, you can use this, but this will result in an implicit scheme. So you have to do a lot of more work. And if you use the left-handed side, you get an explicit method where you don't have to think about any all, just compute. In an implicit scheme, you have to work a little bit more. Implicit schemes are important. Maybe I'll do a video about this in the near future. But for now, just keep this in mind that choosing different approximation rules will give different algorithms. And in the following, we'll use this approximation here I just presented to you. Using this approximation rule, we can now approximate our integral on the right-hand side. But it's just like 1/2 times h. H is just tk plus 1 minus tk times fk plus 1, which is f evaluated at tk plus 1 plus f of k, which is f evaluated at a point tk. And we do this for all k from 0 to n minus 1. So over all time intervals, we use this approximation, and we do this approximation. And this will give us n nonlinear equality constraint. Why is it a nonlinear? Because f is nonlinear. Keep in mind, f is a nonlinear function. In general, it will be a nonlinear function. So this is a nonlinear equality constraint. But this is an equality constraint. This allows us to put it into the fmincon function of MATLAB. In a very similar way, we're gonna treat the objective functional. The objective functional was just the integral over j from 0 to t. And we just split up the integral into very small integrals and use the linearity of the integral and apply our approximation rule for the small integral here. So nothing spectacular happens here. We just apply our approximation rule to the objective functional and get a nice computational approximation of our objective functional. We have achieved a lot so far, so let's put it in a very condensed form. On the left-hand side, you can see the original problem we started with, and on the right-hand side, you can see the discretized problem. I marked some parts of the equations with color to get some matching here and keep you updated what is what. So let's start with the teal one. The teal one is just our objective functional, and the objective functional, well, we just discretized it. You will end up with this discretized version here. So the integral here will transform to a sum on the right-hand side. Similar, we treat the ODE. So the ODE is marked on the left-hand side in red, and it will transform in the discretized version to n nonlinear equality constraints here. So here's just the ODE, and here you have the n equality constraints. For the brown one, for our initial condition, so y evaluated at 0, nothing changes. We just keep it unchanged here. But for our orange one, so our orange constraint here, which is the constraint at the end of our time interval, Well, we just introduced the penalty function here. So the orange equality constraint here just moved here into our penalty function, and the penalty function is now moved into the objective function of the discretized version. So please note that here we are working with vectors. So the control u and the state y are actually functions, while on the right-hand side in discretized problem, we are working with vectors. So this is a very nice overview of the two problems we are working with. So this is the one we started with, and the right-hand side is now the problem which we put into our MATLAB, into our fmincon function. Before we start looking at some explicit example, take a look at the fmincon function for MATLAB in a very general form. So fmincon, as you can guess, it minimizes a function f under some certain constraints. And you can see it here. So we have minimized f of x. X is a vector, such that the following 1, 2, 3, 4, 5 constraints are satisfied. So the first one are nonlinear inequalities. So it's C and CEQ, EQ for equality, are nonlinear functions, which allows us to model nonlinear inequalities and nonlinear equalities. And the number 3 and number 4 are, again, linear inequalities and linear inequalities. Of course, every linear inequality can be put into a nonlinear inequality, but then you will lose a lot of information, because if you know the structure, if you know that you only have linear equalities or linear inequalities, you can do a lot more because you have a lot more information. So that's why the 4 parts are splitted. In a similar way, every box constraint is of course a linear inequality. But this is a very special structure which certain solvers can deal with. So they can be built into the solver to get some specific speed up or specific properties of specific convergent properties or something like this. So this is reasonable to split all necessary or all possible all possible constraints into these 5 different constraints. In the following, we want to use this fmincon function, but for a specific example. And for a specific example, I choose the double pendulum. So in the rest of the video, we will deal with double pendulum and how actually to control the double pendulum, because that's what we wanted to do. Here you can see a standard double pendulum, which consists of 2 bodies which are connected by a joint here and here. And I call the angular θ1 and θ2. The mass is concentrated on this point here with mass m1 and mass m2 and length L1 and length L2. So this is quite standard. And to get the equations of motions, I just apply the Euler-Lagrange formalism, because at the end we need to get our ODE, and the ODE is derived by using the Euler-Lagrange formalism. However, it's not that hard to get this. It's just a bunch of derivations and calculations. But in the end, we get 2 coupled nonlinear ODEs. In red, I marked θ1, θ prime, and θ double prime, because these are the important parameters we want to control and we want to steer. Because with this, we can control our system. Of course, in this form, we cannot use this coupled nonlinear ODEs in our formula, because they don't fit into our definition, into our algorithm. So we do some rearrangement, and the first step is we bring all the second derivatives on one side and the rest on the other side. And we will get 2 equations. They look like this, with some functions alpha1, alpha2, f1, and f2. And the precise definitions, they look like this. What we're going to do now is we drop the arguments, because they are just disturbing and you can't see anything. So if we drop the arguments, things look much more nicer. Now we have something like this. And now you can see this looks like a matrix vector multiplication, and in fact it is. Here you can see it. So we have this nice matrix here, This is our vector containing only the second derivatives, and well, whatever ends up on the right hand side. If you now check that this matrix is invertible, and in fact it is, you can invert the matrix and bring it to the other side. The inverse looks like this. This is good because now we have isolated the second derivatives of theta 1 and theta 2. So let's quickly compute the right-hand side. The right-hand side, if you compute it, looks like this. So G1 and G2 are the components of the first and of the second component respectively. And the precise definition looks like this. I'm rushing through it because it's actually it's not that hard. It's just some calculations, bringing stuff to other side and shifting terms. Nothing spectacular happens here. We still can't use this in our algorithm because we are left with the second derivatives, and our algorithm is not capable of dealing with second arguments, with second derivatives. But we're using now a standard trick. And the standard trick is, I'm pretty sure you've seen this before, is by introducing additional variables. So omega 1 is just theta 1 prime, and omega 2 is just theta 2 prime. If we apply, or if we introduce these additional variables into our system here, we see that we end up with a system containing only first order derivatives. So by making our system bigger from 2 equations to 4 equations, we now are able to get an ODE which fits into our settings. So this vector here, theta 1, theta 2, omega 1, omega 2, is now our state variable. This is denoted by y. And on the right hand side, we end up with, well, whatever ends up on the right hand side. This is called f of y. So this is our right hand side of our ODE, and you can see it here. So now we are able to start our optimization. But before we can start computing, we have to talk about what is the thing we want to control. And the second question is, how can we control the system? Let's start with the second equation. We can only control, in our setting, the acceleration of theta 1, because assume we have at this joint here and here, we have a motor. And this motor can increase or decrease the acceleration of the angular theta 1. And the second part of the pendulum is just swinging freely depending on how strongly you move the first part of the pendulum. So this is the method how we can control the system. So question number 2, check. Question number 1 is, what do we want to control? What do we want to achieve? And I assume that we want to control the system, we want to steer the system in such a way that its outer point x2, y2 is as close as possible to a desired point at time equals 1. So we want to steer the pendulum using the acceleration and increasing or decreasing of the acceleration of theta 1 in such a way that x2, y2 will be as close as possible to xt and yd at time equals 1. So this is our setting. This is what we want to compute, and this is what we want to achieve. But now we have some problems, because we're only working with theta 1 and theta 2. If you look at our state vector controls theta 1, theta 2, and its first derivative. So that you cannot, in the state vector, x and y2 are not contained. But this is not a big of an issue, because we can compute the position of x2 and y2 using our angular theta 1 and theta 2. But nothing spectacular. Just take the sinus and the cosinus, and well, you can see the formula here. If you do this in that way, well, this gives rise to a function g, and I call this function g because it's the function g we had in the very first beginning, where I told you, oh, don't worry about function g, it will be clear from the context later on. The function g maps the parameter y, which lives in a certain state space, to our Cartesian system. And if you remember our optimization definition, we want to control the system in the Cartesian system, not in the state space. So that's why we need this function g of y. Here you can see again the penalty function, which consists of beta times g of y minus the desired point xd yd. And again, g maps from the state space to the Cartesian space. Or to put it in other words, our constraint parameter gt is just our desired point. One could ask, why the hell are we bothering with this penalty function? Why are we doing all this work? Why are we not just putting the state constraint directly into our nonlinear constraint? Because in fact, this is a nonlinear equality constraint. Well, the reason is again in the difference between the state space and the Cartesian space. First of all, the function g is not injective. So you have assume x2 and y2 is at a desired position. Then you can easily set up two different solutions for our, or two different inverse for our function g. You can see them here. You can see the first one here, where the pendulum is moved to the left, and on the right hand side it's moved to the right. Both pendulum satisfies the constraint that x2, y2 are on the same positions here. So, but which is the correct one? I cannot tell you. So the function g is not injective, and this is a huge issue. And that's why we are putting it into the penalty function, because that's in this way we can let the algorithm decide which is the correct one, which does minimize our objective functional. And there's another reason which is more important. If point xd and yd is not reachable, so let's assume xd and yd is put in such a way that the pendulum cannot move at all to this direction, well, you will never be able to satisfy this constraint. And if you cannot satisfy this constraint, well, your solver will say like, oh, it's not solvable, I'm crashing, and you will not get any reasonable data at all. But if you tell him the penalty function has the property, it will bring the algorithm as close as possible to the desired point. So for instance, if the desired point is put like here, the closest the pendulum can move x2 and y2 to these locations is if the pendulum looks like this. This will be the correct solution, or this will be the desired solution. And you see, this is, well, this will work with the penalty function, but this will not work if you put the constraint directly into the nonlinear constraint. Okay, now if you followed the presentation, you will ask me, okay, well, that's okay, I understand this, but what's with the first penalty? Well, what's with the first constraint? We still have a constraint for y evaluated at 0. So this is the so-called initial condition. I'm telling you, you're correct. This is an issue, but in our case, we get rid of this because we assume that our pendulum is at rest for time t equals 0. So it looks like this. And if the pendulum looks like this, well, you know easily, okay, theta 1 must be 0, theta 2 must be 0, and if it is at rest, its first derivatives must be also 0. So in our case, we can simply set, okay, y0 must be 0, 0, 0. Boom, and you're done. And these equations are actually put into the nonlinear constraints, that's correctly. But this will not work for the constraints at the end of the time interval. So as mentioned before, we can control the system by increasing or decreasing the acceleration of theta 1. And we can do this by modeling this into our ODE. So this thing here is the ordinary differential equation, which we just derived for the pendulum, for the double pendulum. And we just add another vector which has a control u in the third component, because if we add a function u or value u to the third component, we modify the value omega prime, omega 1 prime. But omega 1 prime, it's that theta 1 double prime, which is just the acceleration of theta 1. So this is the correct way to modify our ODE. And we call the resulting thing, the resulting function f of y of u. Okay, so this is what we want to model. Let's do some discretization, some notation. We call the discretized function theta 1 will be denoted by theta 1, and in the upper index it will be 0, 1 up to n, because we are discretizing our vectors into n plus 1 different components. And of course we have to do this for theta 1, theta 2, omega 1, omega 2, and u. So this is just a notation, and keep this in mind. We have still to store the data in a reasonable way so that we can access them. And I decided to put it in a big vector in the following form. If we want to use fmincon, we have to put all these discretized parameters, so theta 1, theta, omega, and the control u, into one big vector. And the way I choose is I put theta 1, theta 2, omega 1, omega 2, and u for the 0th component, then for the first component, and last for the nth component. So in the end, our big vector x will be a big vector containing 5 n plus 1 different values. Okay, so this is the way we want to implement this into MATLAB. Okay, now let's start with the nonlinear equality constraint. Recall that for every state vector, which is yi, and fi is the associated evaluation of the right-hand side of the ODE. For every I from 0 to n minus 1, we get the 4 nonlinear equations, which we derived discretizing our ordinary differential equations. And I will show you how to implement this into MATLAB. Let's take a look at the implementation of the nonlinear equality constraints. They are gathered in a function called MATLAB, so of course for my constraints. And this will return two vectors, z and zeq. So c, if you remember the definition of fmincon, was the nonlinear, or contained the nonlinear inequalities, but we do not have any nonlinear inequalities, so the z is just the empty vector. But zeq contains our nonlinear equality constraints. So let's start with the very first initial condition, which was that the pendulum should be addressed for t equals 0. So let's remember our definition of our big vector x. So x1 was theta 1 for the very first time, so for time equals 0. x2 was theta 2 for time t equals 0, and x3 and x4 was the derivatives of theta 1 and theta 2, so omega 1 and omega 2 for t equals 0. And we want them to be 0. So we just say, okay, ceq1 is x1, and this should be 0 because that's what we are checking. We're implementing the equality constraint in such a way that they are all 0. That's the way it is done. So x1, x2, x3, and x4 are the state variable y, y0, and we want them to be 0, and that's done here. So let's continue. Let's move to the more interesting. Let's move to the approximation of the ODE. You can see them roughly here. J and L are some integers which help me to keep track of first of my position inside the vector x, at which time am I, and J helps me to keep track of the equality constraints which are already filled. So now we are looping over all time intervals. And we extract, for easier calculation, we extract yi, which is yk. Okay, there's a slight change of notification here. And yi plus 1, which is yk plus 1, which is denoted by yii. Again, y is a vector of 4 components. So for I equals 1, L is 1. So we have x 1, 2, 3, and 4. So this is our very first state vector. Here is the associated control. And to implement our integration, our approximation of our integration, we do have to get xk plus 1, which is just easy. It's just next vector. It's just the offset of 5 inside the vector x. So that's all to get our information. For easier access, I also wrote a function called ODE right-hand side, which contains 2 arguments, y and u, so state and control, which is exactly the function we just established a couple of slides before. If we plug in y at time at point k and at point k plus 1, we get fk and fk plus 1 respectively, which are denoted with fi and fii. And to get our equations running, we just, well, you can see them here, we just subtract them, and in the end we want them to be 0. This will give us 4 equations, so from j to j plus 3. These are 4 equations. And basically that's all you have to do to get the nonlinear equality constraints working for our ODE. So it's quite easy, isn't it? It's nothing spectacular. We are left with one last constraint. We want our pendulum to be addressed for time t equal big T. So we go to the very last steady state vector and just set, okay, omega 1, omega 2, which are the derivatives of theta 1 and theta 2 respectively, and set them to be 0. And that's basically all you have to do to set up your nonlinear equality constraints. For simplicity, we set our objective function just to be the norm squared. So if we integrate over j, we just compute the L2 norm of the control vector u. And of course, a discretized version looks like this. So let's take a quick look at the implementation. To get our objective function working, we just do something very similar. We loop over all time intervals. We extract the associated controls, so ui and ui plus 1, and we implement our approximation of the integral. So we just sum up ui squared plus ui plus 1 squared, divide them by half, multiply them by h, and sum them up in a value called res1. We do this for time intervals, and this will give us an approximation of the norm squared of u. We are still left with the penalty term. This is also part of the objective function. You can see the implementation here. This is also very simple. We just get the state vector for t equal big T, so y big N. Just get it here. Since we are living in the state space, but the constraints are formulated in the Cartesian space, we have to move to the Cartesian space. This is done in the function angular to Cartesian, which is basically just the function g I introduced a couple of minutes ago. Once we have the position in the Cartesian space, we can just calculate the two norm difference of the desired state to the position of the pendulum, multiplied with beta, and you're done. In the end, we just have to sum up for a resulting vector, for a resulting value, which is just the L2 norm of u plus the penalty term. That's all you have to do to implement your objective function. Let's take a quick look how to put everything together and make it working. We start by defining some global parameters. These are for the algorithm and these are for the pendulum, and fill them with life. Our discretization parameter is set to 40. I also introduced some additional parameters which helps me to keep track of the plotting and get some nice videos in the end. We can take a look at this in a few seconds. Here you can see again the block structure of the solution vector. And now we come to the definition of the fmincon function. We start by setting up an optimization parameter set, which is done by the function optim set. The structure is very simple. First value is a string, which describes a characteristic, a parameter of fmincon, which you can set. For instance, we want our algorithm to be the interior point method. We want to display every iteration. We want to limit the maximum number of iterations to 100. We want to limit the maximal function evaluation to 50,000. And there are many, many more. You can find them in the description of fmincon function itself. There are a bunch of very powerful parameter sets you can define to get your fmincon function working in a very smooth and very nice way. Let's take a look at fmincon itself. It contains a lot of arguments. Most of them are 0 because, for instance, you can pass some derivation. You can pass some box constraints. If you remember the definition in the very beginning, there's a lot of linear constraints. We do not have them, but we have non-linear constraints, and they are passed here. These are the function fmincon, where the non-linear equality constraints are gathered. Of course, we have to pass the objective function, which was implemented in fmin. We have to pass our initial data, and if you want to, you can pass an additional parameter set, which was done, which I explained you before. And it's basically all you have to do to get fmincon working. Now fmincon will do its magic and hopefully will produce a solution to the minimization problem. After the solution is found, we still have to resolve the data because Q will be a vector filled with data, but we still have to fill it with life. And we have to resolve the data. During our structure of the vector X, we can do this very easy. Just loop of I from I equals 1 to n. And well, by our structure, we have theta 1, theta 2, omega 1, omega 2, and a control followed subsequently after another. And you can use them to recover the data. So very simple. Once you have done this, you can do some plotting here, of course, of theta 1 and the control and everything you're interested in. But I also wanted to plot the movement of the pendulum itself. And I want to render this into a video. So I quickly initialized a video file using the video writer command and plot the pendulum. So here x1, y1, x2, and y2 are basically the coordinates you've seen in the description. So these are basically the function g. I just plot them using some nice parameter sets. And in the end, I write them to the video. And once we are done, I close the video. And basically, that's all you have to do to get our optimization of the double pendulum working. And I think this is a very easy and very powerful approach to get yourself in touch with the optimization of ordinary differential equations. Here you now can see a computational result for this given parameter. We set our desired state to be unreachable, so we put it in the upper right, so the pendulum cannot reach it. And you can see how the system is steered to actually get as close as possible to the desired state. So in the end, let's make the problem a little bit more complicated. Now assume that we can also control the acceleration of theta 2. So again, we have a rotor or motor at the joint here. This means that we can control the whole pendulum, which now can be interpreted as the control of a robotic arm. The question is, What changes have to be made to the implementation? And the answer is not many. We just have to add another control u2, because we're now controlling the acceleration of theta 2. And the implementation is, of course, straightforward. I'm not showing this to you, I'm just showing you the results. But this is all you have to do, and this is a very powerful approach, I think, and you can do a lot of stuff with this easy implementation of fmincon. Here you can see the numerical result for the optimal control of the robotic arm, where we control both angulars. We are now at the end of this video. I hope you enjoyed it. I enjoyed it a lot. I learned a lot about optimal control and about MATLAB and how to get things working properly in MATLAB. I hope you enjoyed a small introduction to the fmincon function, which is a very powerful tool of MATLAB. And well, I hope you are well, take care, have fun, and see you around.